Another application of linearization occurs to express those easy equations of kinematics that you're familiar with. So if you have a little ball of mass m above the Earth of mass big M, then the force of gravity is a radial force. It acts along a line connecting the centers of these two masses. And it's kind of complicated. All right, so the way it looks is it's a negative big G, it's a gravitational constant, mass of the Earth, mass of the ball, divided by r squared times a unit vector radially pointing outwards. So little r hat is a little unit vector, and little r is a distance between the centers of these two things. Now, this would make all of your kinematic equations in physics really complicated. And so let's clean it up a little bit. One thing we can do is express it in terms of the height of the ball above the planet. So we could look at something like this. We could use the radius of the Earth plus the height squared. This is still the distance between the centers of the objects. Now, secondly, we can break this up a little bit. Notice that if I put the little m out front, and I have this minus g big M over the radius of the Earth plus the height above the surface of the Earth squared, that this is an acceleration. Just by units alone, you have mass times acceleration, ma. So this is the thing we're going to linearize, and we're going to linearize minus big G M over radius of the Earth plus height above the surface for h equals 0. So we're going to approximate for heights near the surface. We're going to see if we can't simplify this complicated expression and replace it with a linear one. The great thing about linearization is you're always approximating a function by a linear function. Linear functions are easy. No powers, no square roots, no trig, no exponentials, no logarithms. So right now, my acceleration is a function of h. For different values of h, I have different accelerations. I want to linearize at h equals 0. What's my acceleration at h equals 0? Well, it's minus g m over radius of the Earth squared. Right? So I'm going to need a derivative. So the derivative of acceleration with respect to height. And so let's think of this as minus g m radius of the Earth plus height above the surface to the minus 2. And we can write this as 2gm re plus h to the minus 3 times the derivative of the inside, which is just 1. Move the camera a little bit. And so this is the same as 2gm over re plus h cubed. Now I can evaluate this at h equals 0 as 2gm over radius of the Earth cubed. So this is my slope, right? And this is my point. So now I can make my tangent line, or my linearization. The linearization, we'll just use the formula, is 2gm over the cube of the radius of the Earth times, so the difference between height minus 0, that's where we're linearizing, plus the value of acceleration at the surface. So there's that. So what does that mean? Yeah, that's an excellent question. And I forgot to look up all these numbers ahead of time. Well, that's fine. Let's let's look them up. So let's look up gravitational constant. So gravitational constant, let's get that. Blah, blah, blah. All right, so this G is 6.67 times 10 to the minus 11 in MKS units. I need the mass of the Earth, so let's do that. So mass of Earth, and that is 5.97 times 10 to the 24 kilograms. And then I need the radius. Whoops, that's not radius. Radius of Earth. And that's meters. What? Just give me something. Oh, not Myers. Here we go. It's 6,371 kilometers. So it's 6.37 times 10 to the 6 meters. All right, great. Let's calculate these things to gain a little bit of insight. All right. So for this first one, I'm going to have parentheses 2 times gravitational constant, that's 11, that's going to make things small, times m, which is 5.97, to 24, that's going to make things big, divided by the radius, 6.37, e to the 6, cubed, which will make things small. So this is 3.08 times 10 to the minus 6. And what's this number here? Well, let's do, this is a minus 6.67 10 to the minus 11 times the 5.97 to the 24 divided by the radius squared. And that should look familiar. All right. So what's the equation of our line? Well, remember we're linearizing gravity to the surface of the Earth. So the linearization is 3.08 times 10 to the minus 6 times height minus 9.8, or in other words, this is 0.12345. 1, 2, 3, 4, 5. Yep. 308 h minus 9.8. And this is approximately equal to the acceleration based on height above the surface of the Earth. Well, it looks like height doesn't really matter. In fact, if we're just keeping the acceleration to 9.8 meters per second squared, then you would need 1, 2, 3, 4. So you would need 10,000 to 100,000 meters to start altering this number, which means you can go up quite high. You know, a single kilometer would only move this 1, 2, 3, and that still wouldn't be affecting the 8. So you can go up hundreds of kilometers and not appreciably change the acceleration due to gravity. So what this means is that the acceleration due to gravity as a function of height above the surface of the Earth is approximately negative 9.8 meters per second squared. This is linearization. Oh, that was my phone. So there's a great application of linearization that you probably never knew you were doing. But every time you use this for a kinematics problem or a pendulum or whatever, you're using a linearization of gravity.